That's true. Maybe this is for the extended.
Okay, let's start. So welcome back. Really proud to have my student Soumik Ghosh here from Chicago to start us off today. He's going to tell us about a new concept we've been working on for a long time, which we call pseudo-entanglement.
Hi everyone, thank you for having me here. Soumik. Today I will talk about pseudo-entanglement. This is based on two of my papers, which is a joint collaboration with Scott, Boland, Pfefferman, Vazirani, Chang, and Medkar. So in this slide, I will give you a bird's eye view of the things that are going to be covered. So chapter 1 will be some background and motivation on pseudo-entanglement. Chapter 2 will be a description of a concept which we call private key pseudo-entanglement. Chapter 3 will be a description of a new concept from our latest paper, which we term public key pseudo-entanglement. So let's begin. Here's some background. Entanglement is the driving force of quantum computing. It has been studied by scientists both old and new. For instance, it was the topic that won the Nobel Prize in Physics in 2022. But there's still a lot that we don't get about this phenomenon. And in this talk, we will give a new property of this phenomenon. Here's another motivation from the side of quantum gravity. For instance, on Monday, Lenny Susskind gave a very fascinating connection between three different topics: entanglement, geometry, and complexity. How are these related? So quantum gravity theorists believe in a conjectured duality, ADS and CFT, the bulk and the boundary. It is conjectured that these are duals. Object in one of these worlds is dual to objects in the second world. What sort of objects? Entanglement in CFT, for instance, is conjectured to be a dual to geometry in the bulk by, for instance, something like the Ryu-Takayanagi formula. In this work, one way to motivate our results is to say that this property, this phenomenon, is not feelable or measurable in polynomial time. Entanglement is not measurable in polynomial time. So then it raises questions about what happens to the dual of this object. Are the corresponding geometries feelable? Well, if not, then the dictionary, the mapping between the bulk and the boundary, what does it mean for the complexity of this dictionary? Let's segue into our first construction of pseudo-entanglement. But before that, questions on the motivation. So how do we construct pseudo-entangled states? But before that, let's make sure we get some notations first. Entanglement in this talk will be measured in terms of the von Neumann measure with respect to a fixed bipartition. S is the symbol that we will have to denote that. Okay, what is pseudo-entanglement? Just to give you a definition and make it clear, it's two collections of states, psi and phi, indexed by keys k1 and k2. These will be pseudo-entangled if three properties are satisfied. The first, given the keys each state of each collection should be preparable in polynomial time by a quantum computer. Second, say there's two parties. Say there's a challenger and a distinguisher. So the challenger samples one state from one of these collections at random, makes many copies of this state, and sends it to the distinguisher. And the guarantee that we want is that if the key that corresponds to this state is a secret, then no distinguisher running in polynomial time can tell which collection the state came from by looking at many copies of the state. And the distinguisher could be quantum as well. Mathematically, this is what it means. Thirdly, there's a gap between the first collection, for instance, is say high entanglement, and the second collection has low entanglement. So there's a gap between these, the von Neumann measure of these two collections has a gap. Any questions about the definition?
So this is, they're all bipartite pure states shared between the same parties.
Yes.
So when you say you give the
I-
distinguisher, you give them both
Both the parts,
sides.
yes, both the parts.
So this is like weaker than your previous definition because you're fixing a single bipartition.
Yes, we will get to how to deal with multiple cuts and everything else. But for now, let's consider the simplest, most reductive model where I fix the bipartition, and that is like publicly known from.
So from the perspective of quantum gravity, it'd be more natural to have a definition that doesn't involve ensembles of states, which I realize is critical for this particular definition. Can you think of a possible modification of this that would allow you to define it for just without using the ensemble at the key?
Like you mean for fixed states, for instance? That's a great question. I don't know of, how to do that, but yeah, but that's something to think.
Just take the superposition from the keys and the states,
A superposition of.
and then just tracing off the keys will give you.
I guess there might be some questions like questions regarding the preparability of these states and the security guarantees as well. Yeah, but that's a nice question to consider. If there are like single states that might have pseudo-entanglement and still not be the same.
Does it matter for the definition whether the distinguisher is like, you can think of it as like whether it's uniform or non-uniform, in the sense that I could imagine that for every size
Like some advice, let's say.
there's maybe like a quantum circuit, like and a small sized quantum circuit that distinguishes, but just from the description of what's given here, it may be hard to find.
Yeah, that's possible.
So which definition?
Uniform is the thing that we go for here.
Uniform.
Yeah. Okay, let's continue. So this is the definition of pseudo-entanglement. How do we construct these states? Our construction will use pseudo-random quantum states as a sandbox. And these states will be computationally pseudo-random. What does it mean? It means that, say there's a distinguisher, and the distinguisher is given the task of distinguishing between polynomially many copies of a particular state or polynomially many copies of a Haar-random state. And say the distinguisher is restricted to run in polynomial time. Computationally pseudo-random states are states such that there's no distinguisher running in polynomial time that can tell them apart from Haar-random states. And to construct these states, as we will see, we will need some complexity theoretic conjectures, plausible complexity theoretic conjectures. Here's a motivating question. We said that we will start from Haar-random states and construct pseudo-entangled states. So entanglement and let's say the Haar measure, how do these things relate, and how much entanglement do we need to let's say like fool or spoof Haar random states, like spoof the Haar measure. So what I will do is that in this table, I will go through 3 collections of states one by one and tell you if they have high or low entanglement. The first is Haar random states. They have very high entanglement, n almost.
Is n the size of one of the bipartitions?
No, the size of the entire like qubits. So it's like a theta of n here. Yeah. I missed the theta. Yes, it should be. The second collection is T designs. What are these? These are states such that T copies of a state from this collection of states is information theoretically close to T copies of a Haar random state. So these are like pseudo-random in a very strong sense.
Sorry, is this for sufficiently high T, or are you talking about?
Say from T equal to 2 itself, it's there.
True on average.
That's right. And the more you get in terms of T, the better does the variance bounds. And for these two, you have very high entanglement. And like Jonas said, the variance bound, that gets tighter and tighter with like higher. How about computationally pseudorandom states though? For this case, the entanglement can actually be pretty low. Well, how low? It can be as small as slightly larger than log n, and that will be our work. Any questions here?
The log n is to any partition or to a fixed partition?
For now, it's a fixed partition.
A fixed partition, and then you
Like a
can give
n
me a
over
pseudo-random ensemble which has a very low entanglement across this partition,
Yes.
but maybe across a different one they might be much more.
Yeah, for now, yes. We will show how to get this for like multiple partitions as well, a little bit.
Is this again an expectation or sort of? with-
No, like a high probability state. Okay, so how do we get this lower bound of log n, in the sense that could we construct pseudorandom states with even more low entanglement, like sub-logarithmic, let's say, or maybe constant, or maybe zero in? Could we do that? The answer is no. And how will we prove this? We'll prove this by contradiction. This was first observed by G. Levinson. We will leverage the say there's a collection of states that have very low entanglement and that are simultaneously pseudo-random as well. We will leverage the fact that they have very low entanglement to distinguish these states from Haar random states. What's the distinguisher? It's something called a swap test. So I will take 2 copies of this state, which is computationally pseudo-random. I will trace out some number of qubits from each copy, plug those reduced density matrices into a swap test, and measure the probability of getting 0 on the first qubit of the swap test. And then if you do some simple math, then you'll see that the probability of getting 0 is something like this. It's half plus 1 over 2 to the s of rho, but this is the von Neumann measure of the reduced density matrix. So for Haar random states, this probability will be very close to half, almost half in fact. But for states with very low entanglement, where this quantity is log n, this will be significantly deviated from half. So that will be leveraged to maybe repeat the swap test many times, seeing if we get 0. That will be leveraged to distinguish these from Haar random states. And whenever it's like log n or less, this thing will be a 1 over polynomial. So this will give you a significant distinguishing bias when you are distinguishing these things from Haar random states. That doesn't work. You can't have very low pseudorandom, like pseudorandom states with very low entanglement.
Sorry, where did you use the pseudo-random property?
Yeah, so I use the pseudorandom property in this line where I claim that for hard random states, since they have very high entanglement, the bias here will be very close to half. Okay, so just to recap our result once again, the swap test gives you a lower bound. Is this lower bound tight? And the answer is yes, and that's our result. We construct a pseudorandom collection of states that saturate this lower bound that you get from the swap test. Now let's get into the weeds of the construction a little bit. So what we will start with is this following collection of states. These are pseudo-random states, and where these phases are picked by any quantum secure pseudo-random function. And the fact that this ensemble of phase states are pseudo-random was again proven by Gheorghiu and Hoban. So we'll start from there. And now we will do some relabeling. The same state, just with some fancier relabelings to make the bipartition clear and to make the math clear later. So we just diffy up the state into two registers. That's what the bipartition is. Now, just for convenience of presentation, let's try to think of the state in terms of a matrix where we collect all the phases that we had in the state. This is just like a switcheroo from like thinking about a state to this object that's a matrix. It would help us. Why would it help us? Well, now the reduced density matrix across a bipartition can be written very conveniently in terms of this matrix. So this makes our life simple. But this has a one-to-one correspondence with the pseudorandom state. It's really the same thing.
F is not what phase, so F is plus minus 1.
F is 0 or
Plus minus 1 I understand. 0 and 1 I would be surprised.
So it's plus minus.
plus minus 1. Sorry. Yes.
Surreptitiously redefined F to be minus 1 to the previous F.
Right. So the F is the entire phrase. Yeah. Sorry.
Yes. Yeah, okay.
That's fine.
That's okay. I just thought I will learn a new fact about like how to get the two states.
Yeah. This is basically the phase of the states that you saw in the previous. Yes. Sorry. Okay. So more questions? So why did we do this? Well, this exercise was done because now we can write the reduced density matrix very conveniently. Also, the entanglement of the state can now be upper bounded by the log of the rank of this matrix. And this can be seen by Jensen's, for instance. And how do we make the states low entanglement? Well, one naive way to do it is to reduce the rank of this matrix. But doing this in a quantum secure way, to make sure that when we reduce the rank, there's no distinguisher that can feel the fact that the rank is reduced. That would be our strategy. Like I said, we will use a pseudorandom function, but one that has a lot of collisions to reduce the rank of the matrix, just to make sure that things are still quantum secure. So we will construct a new pseudorandom matrix, CF prime, such that the ith row of CF prime is the gith row of CF. And the gi will be a pseudorandom function, but with a lot of collisions. The way we will do it is we will compose two pseudorandom permutations together with this modulus here that will introduce the collisions. Why do we do it in this weird way? This is just to ensure security. And if you just now do a tedious calculation with a bunch of hybrids, and then you'll see that in the end, this is indistinguishable from like a and like you can see this by the collision bound, for instance, for sufficiently like many choices of k. For instance, we can, by tweaking this k parameter here appropriately, we can make the entanglement really small. This k parameter governs the number of collisions in the function. More the collisions, more the state is like low entanglement. And so by tweaking this k parameter and harkening back to the collision bound, the entanglement can be as low as just slightly more than log n, asymptotically more than.
This is a naive question, but how does a lot of collisions get you to low rank?
So because that's how we are picking the rows of this new matrix. Yeah. So lot of collisions means yeah, like a lot of repeated rows. Yes, exactly.
So what breaks when you go beyond log n?
The collision bound breaks. It's like these functions are no longer pseudo-random. Like you can distinguish these from random functions.
And what's the relation between k and the pseudo-entanglement?
I think like depending on k, I guess it's like maybe like choosing k to be log n, like say like log square n directly gives you like a low entanglement of like log square, something like that. Yeah, so yeah, I can't parse right now if like k needs to be like k or like this minus k, but like like there are choices of k that are directly correlated with like how much low entanglement.
I guess it's n over 2 minus.
Yeah, something like
The lower the mod, the more collisions you will get.
yes. More questions? Okay. But there's one important point to note about these functions. Is that these functions are private key. In what sense? Well, if we describe G explicitly to you, if I tell you the circuit that constructs G, then the security of these functions are like broken. The guarantee is no longer there. Because yeah, then you can find out if it's like a 2 to the k21 function or a random function. So the description of the circuit is hidden from the distribution.
If you rewrite G in like usual quantum mechanics language, is it a unitary?
So the way it's written here is that it's like a function.
Yeah.
But for instance, if you use this G to, let's say, construct a pseudo-random phase state and say like pick the phases with respect to G, then like a circuit that prepares that phase state has like a description. That's like a valid quantum circuit. And by like reading off that description, like you can figure out what the function is. It's just like a simple phase. Okay, so this is the construction. We cleverly like choose how many collisions we have in our like matrix, like in the phases, and that gives us lower. And this gives us a pseudo-entangled state across one cut, as I like stressed in the beginning. And the cut is known from before. Moreover, the pseudo-entanglement gap that this construction gives us is maximum. Like we can't go beyond that because of the swap test law. Like n versus like slightly larger. Now to come back to a question I had someone said before, could we strengthen this construction to have pseudo-entanglement across multiple cuts of a state? The answer is yes. So how do we do it? What's the strategy? I won't go into the details of it here, just give you a sketch of the strategy. Let's assume the qubits to be arranged in a 1D line. So what we would do is that we would go from the left to the right of this line, construct pseudorandom matrices at each step, and at each step use freshly sampled pseudorandom functions to smash down the rank of these matrices to make every cut low entanglement. So for instance, say the sweep is from left to right. Say step I is here. I construct the pseudorandom matrix corresponding to the cut here. Reduce the rank of this matrix by pseudorandom functions. And then for step I plus 1, I do the same for the cut here. And I keep going from left to right. What you can see by some back of the napkin calculations, if you actually write out these pseudorandom matrices, that when you are doing this, going from left to right, then if something is low entanglement across this cut, say you have like locked a construction of a pseudorandom matrix such that that has like low entanglement across this cut, then when you are going to the right, doing some rank reducing towards the right, like things towards the right, doesn't change or the construction that you already had locked for this step, like step I. So things neatly work out. And yeah, like I said, this can be just found by writing out the pseudorandom matrices, seeing exactly what they are, and then just like staring. Any questions regarding the strategy?
So this gives you low entanglement across any cut or any cut in one?
That's a great question. So for now, things are 1D. Yeah. But now, for any cut, we can apply like properties of the von Neumann measure, like subadditivity, for instance, to claim that we do have pseudo-entanglement across any cut, with the difference between the two cases being n versus b times polylog n, where b is the size of the cut.
Sorry, have you actually used the ordering anywhere? Like you don't have a notion of a Hamiltonian or anything. So like, shouldn't I just think of these as sets of things rather than like actually arranged on the line or anything?
Yeah, this is just like more of like a yeah, just like we force the thing to have some like geometry, but like this doesn't actually have a geometry. This is not like a
So
1D.
the order you do it doesn't matter.
Yeah.
Afterwards, it does have a geometry, right?
Afterwards, it does. Like
That's
when,
right.
yeah,
So plus at least
that's right.
in this one geometry, you have a bounded rank, and the rank in the other cut is higher.
That's right. Like post what we do, like yeah, then this thing will have a geometry, and then this formula that I mentioned will respect that geometry. But that like post fact, that is true. Yes.
And in fact, there's nothing. No, there's just some function and no state. Right? In some sense.
So you're saying after you've done this, if I now pick some other bipartition which doesn't respect the ordering, I still expect it to have high entanglement across that cut?
Like after I have done this rank reducing, then this thing has a like a hidden geometry, because that's exactly how I reduce the, like this is like a 1D line now, and depending on exactly how I'm cutting that 1D line now, the lower high entanglement will be like, and depending on the state collection, it will be n or like b times polylog, and this b factor will change depending on how
So
we're
I
cutting.
can only, okay, so there's another way to say this, that I can only get the entanglement to be small across a polynomial number of cuts, which are the ones that respect this ordering, but there's still an exponential number of cuts where it's high.
Yeah. It could be, could potentially be high. Like
So
we don't.
generically it should be, right?
Yeah.
So basically, you're having fixed product state.
In some sense, right? Yeah. In some.
Just a bit.
Yeah.
One could ask, even, I mean, your bipartitions are kind of come from a tensor product structure, right? And you're partitioning that tensor product structure. In principle, of course, I could ask, I have a 4-dimensional Hilbert space and I want to factorize it in any way, right? And there's like an infinite number of ways. So can we say something about that? Like, because how many?
My intuition. Yeah.
Structure, you can just say, okay, I can just try to factorize my Hilbert space in all kinds of ways.
Let me show you the next slide where I talk about like a 2D geometry. Maybe that will be like a yeah. that might help with your question.
Okay.
Yeah. Let me show you the next slide, and then we can get back to this. Okay. So this is for 1D. What if now we consider some sort of a 2D geometry? Let's say like a grid of qubits. Could we think of our like starting qubits to be like in a grid, for instance? Well, the point is now we can use the same strategy by thinking of the grid to be actually a 1D line. Like for instance, just like snaking through the grid like this. And then we can do the same like sweep from left to right and like reducing the rank to get like. So I think that for higher dimensions, something similar should be true. Like you can just think of the entire thing to be like a 1D line and apply the same
I
strategy.
read something different. I mean, here you always have like n qubits, right? And then there are a discrete number of partitions. But in principle, if you don't assume any underlying tensor product structure of your space, you can just partition, say, any 4-level system into 2 qubits in an infinite number of ways.
No, but
And then one would try to ask, can one kind of, sorry?
Yeah, right.
If I just pick a random slice of my Hilbert space, the states that I started from will just look like a high random
Okay,
state.
but say I have some ensemble, pseudo-random ensemble, will there always be a cut where most of them are highly entangled?
Yes,
It's not
most,
obvious.
I think most cuts will have most states maximally entangled just by counting.
Right, I think
Really?
there's a one-to-one
super
correspondence.
exponentially many cuts I
Yeah.
can make, right?
Sure, but it's not. I mean, counting completely neglects the linearity of the whole
But
problem.
think of this as just applying a random unitary to the Hilbert space, right? Because you're taking a totally new tensor product structure, and so that has to be a hard random.
Right, but I have a fixed pseudo-random ensemble, right?
Yeah.
So I have a fixed set of vectors. I rotate them all the same way. We will have some
Oh,
condition.
okay, you're not.
It's not that you. Well, I mean, there will be some constraints. I'm just wondering what they are. But it's not right. I mean, if I give you 50 vectors in a 4-dimensional space, they will have fixed angles.
Yeah, I think at high end you can count your way out of that. But let's maybe do this later.
Okay, no, I thought this could be an interesting conversation.
Yes, like a follow-up question.
Yes.
So just now you told me that the 1D construction gives you all cuts. So why do you even think about it?
So the way to like the reason to go to 2D is just to like stress the fact that this procedure that we have is quite generic in the sense that we could think of qubits to be in a 2D line, like a 2D grid as well. And the same strategy of like reducing the rank by thinking of things to be like in a 1D line still works.
I thought we just started from some collection with no ordering.
We did, yes. That's right. That's right.
just saying this.
Yeah, like this is just saying that like thinking of the qubits to be in 2D and then employing a same strategy still gives you the same.
So it preserved the geometry, like when you arrange it.
Yeah, like the cuts, because the cut now would preserve the 2D geometry. Like the size of B, for instance, now would depend in some sense on the geometry.
Yeah. So the new size of the cut is still the size of the cut in this original geometry.
In this like 1D type geometry, yeah. The point of this picture and the point of this like procedure is just to say that, say I don't have any geometry that I start with for my qubits, I could think of any spatial geometry that the qubits are in, do the same procedure for that, this like sweeping from left to right, by thinking of everything to be in some sort of like a pseudo like 1D geometry. But let's discuss this later. And there's one more construction where we, let's say, don't even need to do this sweep from left to right. We can just like get maximal pseudo-entanglement no matter what the cut is just from the get-go. And that's this like subset phase state construction, which I will not go into here. See this very nice Simon's colloquium on this, on like quantum pseudo-entanglement, where this was covered in detail.
So for this subset construction, you need pseudorandom permutations, but for your sweeping, you just need pseudorandom functions.
No. For sweeping, we still need like pseudorandom permutations, just because those like reducing the rank procedure, the way we repeated the rank was through. So we still need pseudorandom like permutations. And what are some applications of the private key construction? So anything that's as hard as testing, if your state has high or low entanglement, should not be polynomial time. So this gives you time complexity lower bounds on a bunch of things like spectrum testing, Schmidt rank testing, testing matrix product states, for instance, these types of tasks, which all have this flavor that they're trying to test if things have high or low entanglement. And it also gives you time complexity lower bounds and distillation protocols, where the goal is to give me some, distill some bell pairs from the state I start with. And the point is that low or high entanglement means like you can distill that many bell pairs. And that shouldn't also be polynomial time, because if you do that, that's a distinguisher just by counting the bell pairs. And there's also more constructions of pseudo-entanglement. Like, for instance, check out this one, which came out recently, which talked about generalizing this concept to mixed states, and their states can be preparable by local operations and classical cognition. I will now segue into the public key part of the construction, but before that, questions on the private key part.
Yeah, do you need this assumption, this computational assumption, to get these results?
Yes, we do. Like we need the so all of these are like time complexity lower bounds. So that itself is like a computation statement. The fact that
Did you mean do you or does one?
Yes, exactly. I don't think we know that yet, that we need an assumption for sure. Certainly these constructions need
Well,
an assumption.
okay, yeah. Sure, yeah. But yeah, are there other ways of
I don't know of anything.
making this assumption? Sorry.
So quickly confirming that the same for the LCC-based result.
Sorry?
Does the LCC-based result on the next day also have the time?
Yeah, time complex. Yes. Yeah, these are all like computational results. Yeah, fundamentally talk about like bounded time distance. Okay, so for the public key construction, here's one reminder to start with. The private key construction had a feature, and the feature was that these functions that we had to reduce the rank of different pseudorandom matrices, these were private. The descriptions of these were private. So that meant that the distinguisher didn't know the circuit description of the circuits that prepared these pseudo-entangled states. And the security hinged on that fact. So could we strengthen the construction to consider pseudo-entangled states that remain pseudo-entangled, like secure, even when the description of the circuit is published, it's public? One motivation to study this question is Hamiltonian complexity, because if you have like public circuit descriptions, then you could just apply Kitaev clock type mappings to map them to descriptions of Hamiltonians. And then you could ask if the ground state of those Hamiltonians have pseudo-entanglement. And this was first studied by Gheorghiu and Hoban, for instance. Questions of this? I will get back to this later, but before that, let me tell you about the public key construction. So what is our result in the public key setting? So we will use a cryptographic conjecture that gives you secure public key post-quantum cryptography. And with this, we will construct pseudo-entangled states again that have maximal entanglement across all cuts with, say, this dependence on the cut size. And the previous work before us, for instance, had like constant pseudo-entanglement gap across a single cut. And this was by Gheorghiu and Hoban. How would we do this? The procedure is once again very similar to before. What's the procedure again? So we start with the same ensemble, like pseudorandom phase states. And then we do the same thing. We construct the pseudorandom matrix. And then we use functions to repeat the rank of the matrix. There will be two cases here, though. In the first case, the function will be 1-to-1. In the second case, the function will have many collisions. I call this lossy, like 2 to the like something like a 2 to the k1 function. And the property that we would need from these functions is that even when a description of these functions is public, it's hard to tell apart which case we are in. If the function is like 1-to-1 or lossy. And just a type check, we are reducing the rows of this matrix. So the function will be like this is the domain and this is the codomain of the function. And yeah. Questions here. This is the strategy in short. Now the rest of the slides will concern on how to construct these functions. LWE is the primitive that we would use to construct these functions. And the next few slides will give you a brief primer on what it actually is. I will be a little sloppy with the parameters because this is like a qualitative picture of this crypto primitive. If you want the gory details of like every parameter here, then refer back to our paper. So what is the task? What is the conjecture? The task is something like this. Say I'm given a matrix A that's public, and with it, I either sample a random vector or apply this matrix A to a secret string S, see the result, and then corrupt the result with a Gaussian noise, and then send you the final vector, this corrupted vector. And say your task is to distinguish between these two cases with this, like these priors. You know the matrix A and you know like this thing, which is promised to be like one of the two cases. Now, there are many flavors of this crypto primitive. The standard conjecture says that every polynomial time quantum computer, even when it's given many samples of this kind, cannot distinguish between these two cases. S here, note that is a fixed secret. There are stronger versions of this conjecture, which says that not only can the distinguisher not distinguish between these two cases, but the distinguishing bias would be extremely tiny. Any questions here? Yeah. Note here that we are working on like a field of size Q, no longer a binary field. And the length of this secret string, there's a wide range of parameters of the length of this secret string such that this conjecture is still plausible. So like we have some leverage on like changing the length of the secret. What is our goal? To recap again, we want to construct 1-to-1 or lossy functions using this crypto primitive. How would we sample a 1-to-1 function? We would just sample a uniformly random matrix U and then say define a function like this. And how would we, and this would be like a full rank matrix, for instance, with high probability. Why is there a blow up in the codomain size here? Once again, one way to think about this, and this becomes clear with the back of the napkin calculation again, but one way to think about it is we're switching from binary fields like to fields of size Q. And the size of Q in like for things to be secure would have to be very large, like in the size of n, for instance, like 2 to the n. So there's a blow up because you need to write down Q. So that's how you sample a 1-to-1 function. How do you sample a lossy function? Well, you sample like a lossy matrix BTC plus E, where E is like the Gaussian noise that you saw from before. And this lossy matrix is it's like a low rank matrix. And the way we make the rank low is by tweaking the parameters in the the conjecture that we saw in the previous slide, like tweaking the size of the secret, for instance, and some more parameters. And doing that, there's a way to do that, still remains secure, but get a very low rank matrix here. In some sense, this is the, to mentally map, this is the step that corresponds to the collision bound type calculations for the private key construction, just by tweaking the parameters of this concept. And there's a result by Pikert and Waters, for instance, which says that distinguishing between these two types of matrices is as hard as breaking the crypto primitive. But there's a problem with constructing functions like this. I think the problem is pretty right there. It's the problem with type checking. Now the codomain size has blown up because we have switched from finite fields to fields of size q for things to remain secure. But to repeat the rows of the matrix, we need the domain and codomain sizes to be the same, like a very silly type check. And that we don't have here. How do we do that? Well, we do it in a very simple way. We use a hash function with nice properties to then hash down the codomain size from this very large one back to what we need. Now, doing this has a cost. The cost is that it's fine for the lossy function, because if you are hashing things down, the number of collisions can only go up. So it will be more low entanglement, which is good for us. But for the one-to-one function, when we are talking about the high entanglement case, let's say, hashing the rank down will introduce new collisions. But the point is that there's still not a lot of collisions in the one-to-one case. And this you can see from a bookkeeping type proof that we do in the paper, for instance. So what is our result again? If you now construct these functions and do the same thing, repeat the rows of the matrix using these functions, then we get maximal pseudo-entanglement. If we have the standard conjecture to be our starting point, then we get pseudo-entanglement with a polynomial gap between the low and high entanglement cases.
So how does the sub-exponential versus standard translate into entanglement?
Yeah, the sub-exponential hardness. So the stronger conjecture you go, the higher is the pseudo-entanglement gap. In this,
I guess I'm asking how that happens.
how that happens? So, yeah, the strengthenings of the conjecture are you can think of these as being related to the size of the secret string that we are hiding. So if the secret is too tiny, say log n or something, then there's simple brute force search procedures to get back the secret. And the sub-exponential conjecture, that kicks in when the secret is polylog size or something like that. And I didn't go into the details of this, but if you just write everything down, do dimension checkings, type checkings, construct the matrices that I showed in the previous slide, then you'll see that if you have tiny secret sizes, polylog n, for instance, then you'll get matrices in the 2 to the k1 case that are extremely lossy, has a lot of collisions. And if you repeat the rows of your pseudorandom matrix with these new functions that you construct from the lossy mode, then you will see that it has very low entanglement. But for that you need the sub-exponential hardness, because the standard one needs larger secret sizes. Did that make sense? More questions here? And how do we generalize to, let's say, once again, a geometry? Well, we like mentally think of the qubits once again to be in like a 1D line, and then we do the same sweeping from left to right and then hashing down the right, just as we saw in the prior videos. Here there's a small problem though, which we solve in the paper. I won't have the time to get into the details here. So when we were actually doing the sweeping, what happened in the private key case was that the functions were exactly one-to-one, like for the high entanglement case, let's say. And so you didn't encounter the problem of like the rank getting lower and lower when you were doing like the sweep from left to right. But here the functions are not exactly one-to-one. The functions are approximately one-to-one. There are spurious collisions now that got introduced because you hashed down the rank. And so there's a problem that you need to focus on of the collisions being compounded when you are like daisy chaining these rank hashings. But we show that they don't really compound. So things are still fine. This strategy still works. What are some applications of the public key construction? Well, one application, as we saw in the motivating slides, is that it says something about the ground states of certain types of Hamiltonians. If, for instance, say, I give you the description, a classical description of a Hamiltonian H, and I ask you if the ground state of this Hamiltonian has high or low entanglement. We show that that should be a hard problem, as hard as breaking this cryptographic. And how do we do that? We can just use these circuits that we constructed. Now the circuit descriptions are public, and then we can just put these circuits through different flavors of that clock constructions. Note that these things are no longer pseudo-random states, because for both the high and low entanglement cases, the circuit has a polynomial sized description. A high random state can't have that. But still, like one collection has high entanglement, the second one has low. Any questions here?
Do you assume here that you know the ground state energy?
I don't have any statements about that here. Just like the task is just to see if it is high or low.
Right, but so you're just given an arbitrary Hamiltonian H, the ground state, it may be frustrated or frustration free.
Yeah.
Okay.
It's a weight split, it's frustration.
Okay, then you know. Okay, that's the answer.
Yeah, the properties of the like the type of Hamiltonians for which these are hard will be the same type of Hamiltonians for which you have those nice properties from the K-type clock construction. So depending on what flavor of clock construction you use, you will have that type of properties.
And this is a property of both the Hamiltonian and the tensor product structure, right? And so it's like decide whether it's low or high entanglement given a computational basis or something like that.
I didn't fully get the question, but let's come back to that later after that's like a couple of slides.
What is the upper bound on the complexity of this problem? Do you know?
Like you mean
containment?
So it's definitely contained in this like QSCK type classes, like for instance, like this paper by Gheorghiu and Hoban studies.
Thanks.
Okay, so this is one application of public pseudo-entanglement. How about some future directions now? Well, there could be more constructions of pseudo-entanglement. For instance, there's like subset state-based constructions. Check out these papers, for instance, for that. And like I said, the Hamiltonians we get are just like you pass the circuit like blindly almost through some K-type clock constructions. But could you get like more physical Hamiltonians, let's say, like Hamiltonians with larger spectral gaps, like more geometric locality? Yeah. So that, like things that condensed matter theorists care about more. And could we get pseudo-entangled states that are compatible with holography? Well, this is the content of the next talk by Lisa.
Commenting question, so for your second last opening question, I mean, if you apply perturbation theory gadgets, they normally preserve like the low energy space, so presumably you get something for free that way?
Like you mean, say I have like a circuit description, then I apply some sort of.
We have a local Hamiltonian, and then you could use perturbation theory gadgets to simulate that.
What sort of properties would say that Hamiltonian has, like large?
No, for example, like if you layer qubit 1 to an hour, right, like these simulation results, basically. So you could simulate the low energy space using, say, Heisenberg model 1, certain types of lattices, for example.
I see.
So,
Which question was the
just able
second?
to plug that in, right?
Which open question was the second?
Yeah,
Let me go back to the slide.
fancy circuit Hamiltonian. That one. I mean, Toby was here, I don't know if he is.
Yeah, the second question. You can make geometrically local Hamiltonians.
Oh, no large stuff we have.
Yeah. Oh, no gap, I'm not talking about gap.
I see.
I'm not talking about
But
gap.
like geometrically.
Yeah, if you just want like
I see.
more physically motivated Hamiltonians.
Oh, cool. I see.
And they can be geometrically local as well, like on the lattice.
By some sort of a perturbation theory.
Yes. And my second, my other question was, I mean, this goes back to Hari's question and also to the gravity question where you don't want an ensemble. Like, I mean, this sounds a lot like QMA2 versus QMA, right? If you can prove that, say, QMA2 equals next, then certainly there's no efficient way to, given a quantum state, to distinguish if it's entangled across the current.
Yes.
And it won't give you a fine-grained, like, lower
Yeah.
bound on complexity, of course, the way maybe your result does, but.
Yeah, that will be one way to like justify more that like finding if a state has like high or like low entanglement, like that can't be like measurable in polygon.
So this, I'm not sure this makes sense in the context of your construction, you can ask anyways. So do you know of any properties of a Hamiltonian that under time evolution, you know, take the corresponding unitary, you would generically go from non-pseudo-entangled states to pseudo-entangled states, pseudo-entanglement generating time evolution, Hamiltonian time evolution?
So I don't, but I saw a recent paper on pseudo-entanglement like a couple of days back, which was studying some sort of a phase transition. Exactly, like seems like very similar to like the thing that you asked. So yeah, it was by like Matteo and someone else. But yeah, like probably people have started studying something.
So I'm trying to understand. Don't EFI pairs give us pseudo-entropy and hence pseudo-entanglement?
They would give you like, I don't think they give pseudo-entanglement per se.
Once you get an entropy difference, I mean, you take the purifications and.
If say you get a difference and then you take the purifications, like I don't think so one of these guarantees would break down, like the security guarantee or maybe.
So they're computationally indistinguishable.
Yeah.
And they have L1 difference or entropy difference.
But when you are taking the purification and say you're like sending the entire system now to the distinguisher.
The purifications, you want the purifications also to be computationally indistinguishable.
Yeah. Because for the blueprint that you suggested, a potential distinguisher could leverage the purifying register to distinguish between the states that type of states that can be constructed.
Can you do multi-part entanglement measures?
Oh, that's a great question. I don't know because the measures get pretty hairy.
Yeah. I mean, pick one. A high random state.
What's the best multiple?
The geometric entanglement.
That's yeah, that's a good.
Like one, this sort of because you don't have the ability to sort of control entanglement across many cuts at the same time. I don't think it follows trivially from your construction.
I don't think it does. Yeah, but that's a nice solution. Yes.
Okay, I think we're going to take all the rest of the questions offline. And thanks, Soumik, again.